This building is defined by precise geometric boundaries, specifically the interplay between polygons and circles. Calculating the exact perimeters and areas of these shapes is a mandatory first step in architectural engineering. Before we can calculate those dimensions, we rely on a core geometric axiom: all circles are strictly similar. Regardless of their absolute size, they share the exact same shape. We measure the scale of these circular forms using two primary components. The circumference is the total outer perimeter, and the diameter is the linear width straight across the center. Because all circles are geometrically similar, comparing any circle's circumference to its diameter always yields a strictly proportional relationship. This theoretical figure, circle 2, highlights its circumference in red, C2, and diameter in blue, D2. Scaling up to circle 3, the structural ratio holds. Circumference divided by diameter always equals a universal constant, K. This unbreakable law of geometric similarity allows us to calculate exact dimensions in any circular system. We define the proportionality constant, K, as the unique positive constant, pi. In Theorem 8.4.1, isolating circumference derives the formula C equals pi times diameter. Because radius is half a diameter, substituting d with 2r gives the equation C equals 2 pi r. Numerically, pi is an irrational number. Because it is irrational, pi cannot be represented exactly by any common fraction or terminating decimal. When solving equations, leaving the symbol pi in your final answer is the only mathematically valid way to state an absolutely exact result. Practical engineering, however, requires physical measurement, forcing us to use approximations. We commonly represent pi as 3.141592654. Theorem 8.4.1 provides a perfectly exact analytical formula, even though real-world application relies entirely on irrational approximations. Often, we do not need to measure the entire circumference. Instead, we isolate a specific segment of the boundary, known as an arc. Every arc has a degree measure, which is purely an angular fraction relative to a full 360-degree rotation. We contrast this internal angle with its linear measure. Linear measure is the actual physical distance along the curve, verified using physical units like inches or centimeters. Theorem 8.4.2 provides the mathematical bridge to convert an angular degree into a linear distance. In this diagram, we separate the internal degree measure from the external linear length. An arc's linear length is exactly proportional to the fraction of the full 360 degrees it occupies. To find the final length, we take this angular fraction and multiply it by the total linear circumference of the circle. Theorem 8.4.2 translates abstract rotational angles into tangible, measurable physical distances. In example 4, we start with a circle possessing a precise radius of 7 inches. We're given a linear arc measuring exactly 45 degrees. The target of our calculation is the remaining outer boundary, the major arc ABC. We find the degree measure of this major arc by subtracting the 45-degree minor arc from the total 360 degrees, yielding 315 degrees. Applying Theorem 8.4.2, we establish the fractional ratio for our major arc as 315 over 360. We substitute our 7-inch radius into the standard circumference formula. This gives us a total exact perimeter of 14 pi. Multiplying our angular fraction by the total circumference gives us the exact algebraic length of the major arc. We then convert this exact algebraic formula into a physical length by substituting an approximate decimal value for pi. Any complex perimeter segment can be mathematically solved by correctly isolating its proportional angle relative to the whole. A limit represents an absolute numerical measure or physical boundary that a system cannot exceed. In circular geometry, we often calculate an upper limit, the maximum possible dimension an internal feature can possess. This diagram from example 5 allows us to test this. We are looking for the absolute maximum length of a chord inside a circle with a defined 5-centimeter radius. A chord is any straight line segment whose two endpoints both lie on the circle's outer boundary. Notice the parallel red chords. As they are drawn progressively closer to the center of the circle, their lengths strictly increase. The upper limit exists at a precise spatial location. The maximum length is achieved exactly when the chord intersects the center point. This unique central chord is formally defined as the diameter. We calculate the final numerical upper limit by doubling the 5 centimeter radius, establishing an absolute maximum chord length of 10 centimeters. Irrational proportions, rigid angular fractions, and absolute structural limits interlock to create a perfectly bounded and predictable system of circular geometry.